Okay, so we have completed motion correction and CTF estimation. And to be honest, we haven't let users in the simulator change many options in the same way that in normal data analysis, you're not changing a lot of options related to motion correction and CTF estimation. Now we're at the level of particle picking, and this is where user choices will matter more, and that will help users understand what's happening with cryoEM. So we're now down the next row here into auto picking. And so auto picking is what Reliant calls particle picking using different automatic programs. There is a picking approach called Laplacian of Gaussians, which is a sort of shape-based particle picker. There is one that uses 3D references or 2D class averages for picking, and there's also a helical picker. In our case, we are just using the Laplacian of Gaussians. So just like other jobs, green means users can interact with it. So now it's asking for what micrographs to use. In this case, auto picking is considering the CTF. So this needs to be, the input here needs to be the output from a CTF estimation job. So we will now have, you see that it shows you different choices though, because Reliant is showing you all inputs that are compatible with the input of auto picking, which is micrographs. So in our case, let's look at CTF find output. These are the output from CTF estimation, and now we have a star file. Again, star files are these metadata files that have increasing amount of information besides just the name where the actual data lives, but also extra metadata. So in our case, we input that, and then now this default option, or this option down here that's already says yes, is use Laplacian of Gaussian. So now we go to the next tab. Here's where now you have choices. And so these three green choices are what you all will be able to choose and see how it affects picking. So what you have in Laplacian of Gaussian is a choice of a minimum diameter and a maximum diameter to consider during picking. And then you also have a threshold. So the threshold you can think of as if the threshold tells you if you're going to be stringent or relaxed in what you select. So negative values takes more, 0 is it takes about half, or it's halfway between -1, and then 1 is going to be more stringent. So let's use these values to start. And if you were to click through the rest of these tabs, there's no other green options here. So this is what we have here, and now we can click run. So this job is going to be picking particles using diameters as the choice. And this will show you that it's possible to pick particles this way, again, without a reference in mind, just with diameters. You'll also see that's not as good as other particle picking that uses references because it doesn't know what it's looking for. It's just using sort of rough diameter and shapes. And so the options as the end user here, you want to try and optimize the picking to be the quote best it can be, meaning the least number of false positives, and we'll look at those in a second, and the sort of picking most of the real particles, and so the least false negatives as possible. Okay, the job completed. You see here it says it from 6 micrographs it picked 2,000 particles, and on average there were 400 particles per micrograph. This already sounds like a lot, so let's take a look. So again, you click on the job, and then you click on this display. And now we can look at different outputs. So if we look at, there's a log file that gives you information about particle picking, but really the most relevant information is in this output star file. So if I click this, it will now show us a few different things. So for each micrograph that it analyzed, the picks and also the CTF. And so let's just, because we haven't looked at it yet, let's look at the CTF. So here it tells you the CTF it estimated in angstroms. So again, 10,000 angstroms is 1 micron. So this was about 762 nanometers to focus here. So let's look at this. If you click on CTF, it shows you the fit is in this top left. This is what it thinks the defocus is. The bottom part is just the micrograph. So these are all the tone rings. And then this top right is the circularly averaged power spectrum of the micrograph. And in principle, these should all line up and agree very well. That looks nice. Okay, so we close that. Now we can look at what got picked from this micrograph. It says it picked 463 particles. And this is where you have to, as an end user, really decide what is a particle and what isn't. So this is the micrograph. This is a proteasome. The proteasome has sort of donut top-down views and then barrel side views. And now if I move my mouse, all the pics will be populated. So all the green circles are what rely on picked as particles. And you can see it picked a lot of things. And it's honestly a little confusing now to see what was what because there's so many circles. And to help you see, if you right click and say reload, they all disappear for a second, and then once you move your mouse again, they'll reappear. So what we want to look at is how it did with picking particles that you can really see with your eyes. So let's do the reload again. You can see this one is a single particle, a barrel. And there's a barrel right here, but there's 2 picks. And so that's one example of it not picking correctly. We know that's one proteasome is that one barrel. It should not be 2 picks. Nearby, you can see other things. So straight above here, this doesn't look like it's on a particle. So let's take a look. Let's reload the coordinates. Yep, that's not a particle. That is just empty ice in between particles. And we can continue this on and on. And again, that's one here. This is in between particles. So you're trying to minimize open ice getting picked and any aggregates that show up. And you're also trying to make sure it's picking the middle of single particles. So optimizing this can be for a later movie. We'll take this as is for now. So if we close this, you could look at more images if you would like. If I click on this one, it'll also show me the images. This is a really good example to show you what it shouldn't look like. So for instance, this is a big piece of ice that was picked. Then you also see this empty area in the middle where there are no particles, but there are particle picks. And you'll be up to you to figure out if this is okay or not for subsequent analysis. But typically we try not to have this come into the pipeline. Okay, so let's close this. And now we will be done with auto picking. After auto picking, the next step is going to be particle extraction. So if we go to particle extraction, we have 2 input data streams that we're going to keep track of. One is which micrographs you're going to use, and then what coordinate or what picking run are you going to use. So for us, the micrograph run will be just the output from CTF estimation, which again is a star file that points to micrograph images, but also keeps track of metadata related to the defocus of each micrograph. And then we also have coordinates, which will be which particle picking run do you want to use. So for us, we only have one run, and we'll include it here. So we have these 2 choices. The next is going to be what box size of particle do you want to cut out of a micrograph, and do you want to rescale them? And so particle box size in pixels is literally taking a box of something out of the micrograph, and we'll be creating what's called a particle stack later, which is going to be thousands of little boxes of particles all cut out together. You have to figure out the choice of this parameter of 100, 200, 300 pixels. So again, this is in pixels, and we'd have to figure out what that means in angstroms to try and understand how that relates to the proteasome size. We will pick 200 right now. And the only other option we have is rescaling. And so rescaling means taking this particle that was cut out, let's say at 200 pixels, and then rescaling to a different pixel box size. So let's say in this case, if it went from 200 to 50, it was binned by 4 because it had to go 4 times. It had to shrink the 200 4 times to make it into 50. For now, we'll say no, but these are things that you can explore later. And nothing else is green here, so now we're ready to click run. So in this example, we are now getting the extracted particle stack that matches the picking run and CTF estimation run that we just had. And now it'll give us what we call a stack of particles. And so here it is giving you some information about what it found. If we look at the standard output file, it's telling you that we have pixel size of 0.91 angstroms per pixel, and that it has 2,774 particles And these are all in particles.star. And again, remember, these star files are just text files, and that this particles.star is pointing to extracted particle images along with metadata. And so in this case, when we extracted particles, we are taking the particle out of the micrograph, and we're also, for every particle, keeping track of what defocus it had from the CTF estimation job. So we're getting this increasingly larger text file here for particles.star. We can take a look at this. So if we go here and click on particles.star, let's only look at a few here. So let's look at 10 particles. And if I click display, these are the particles that it cut out of micrographs. And you can tell they're very fuzzy, they're very high resolution, meaning they're kind of hard to see what's going on. You still can see these are the donut views. So this is a donut view. The other one's a little bit harder to see. Maybe there's no particle, or maybe I'm not sure what's happening. But these are the extracted particles, and that we're going to use these images here, plus their CTF information to then do 2D classification and averaging.